Okay, so in this video, we're going to be looking at general normal distributions. So by the end of this lesson, you'll be able to have an idea of how a general normal distribution is different from a standard normal distribution. Understand and calculate the z-score for values in a data set. Use z-scores to compare scores from different data sets. Use the empirical rules for normally distributed random variables to solve problems. And solve probability problems involving normal distributions. So let's have a look at the first part of today's lesson. The difference between standard and general normal distributions. So in a standard normal distribution, the mean is 0, the standard deviation is 1, and points of inflection are 1 standard deviation away from the mean. So at z is equal to plus minus 1. Oh, and that should say the area under the curve is equal to 1, and therefore it is a probability density function. Now, in a general normal distribution, the mean is just the mean. It might not be 0. It could be 23. It could be minus 15. Okay, the mean is whatever the mean is. Same with the standard deviation. The standard deviation is not necessarily 1. It's just whatever the standard deviation is. It could be 2.7. It could be minus. Oh, actually, standard deviation is never negative. It could be 7. Okay. Points of inflection are also 1 standard deviation away from the mean, but instead of the z-scores being plus minus 1, we've got x. The score itself is equal to the mean minus the standard deviation, and at the mean plus the standard deviation. Okay, so 1 standard deviation above and below the mean. The area under the curve for a general normal distribution is actually not equal to 1. It's actually equal to sigma, the standard deviation. So in that case, it's not a probability density function. So in order for us to make it a probability density function, the area under the curve needs to equal to 1. So what we're going to do is we're going to make adjustments to the PDF of the standard normal distribution, and then make it into a general normal distribution with an area that is equal to 1. So it becomes, so the general normal distribution is a PDF. So here we have, let's have a look at the very first one. Okay, this is the standard. This is the standard normal distribution. Okay, where the area under the curve is equal to 1. The mean is 0. Okay, the mean is where the highest part is of the bell curve. And the points of inflection are both 1 standard deviation away from the mean of 0. At z is equal to minus 1 and 1. Okay, so what we need to do is we need to make adjustments to this curve so that the general normal distribution will also have an area of 1. Because in a general normal distribution, the standard deviation is just sigma, whatever the standard deviation is, and the mean is not necessarily 0. It could be any other value. So in order for us to do that, what we need to do is we actually need to stretch. We're going to stretch the normal distribution horizontally by a factor of sigma. Okay, so now the standard deviation is just whatever the standard deviation is. It's just sigma. It's not 1. But when we do that, we can see here that the area is no longer equal to 1. So in order for us to make it equal to 1, we actually need to compress. We need to push this down. We need to compress the bell curve by a factor of 1 over sigma. So we're going to compress vertically by a factor of 1 over sigma. Okay, and when we do that, now it has an area 1. Now area under curve is 1. And now this is a PDF. Okay. So we can see here, right? I'm just going to go back to this. We stretch it horizontally. So it needs to be x over something because it's horizontally. So we're relating to the x-axis. We're dividing it by sigma. So we're stretching horizontally by a factor of sigma. And then here, we are compressing it vertically by a factor of 1 over sigma. Okay, so if it was y over 1 over sigma is equal to this, we just bring that across and we get y equals that. And we do that to offset what we just did with this, so that our area will go back to 1. Now, what we have here is a general normal distribution, where the standard deviation is just sigma, but the mean is still 0. So what we want to do is, because practically in real life scenarios, the mean is not usually 0. Okay, usually the mean is greater than 0. So what we're going to do is we're going to move we're going to shift the entire curve to the right. So I'm going to just shift to the right by mu, the mean. So when we shift it to the right by mu, this mean here is now shifted to the right, and that's the mean, mu. Okay, so this here, this is called the general normal distribution. And it is a PDF because the area under the curve is 1, because we've seen here that the area of this underneath that curve is 1. We're just moving it somewhere else. Okay. So let's have a look at how to understand and calculate Z-scores. So the Z-score is the number of standard deviations. The score is from the mean. So what I mean by that is, if we have a look at this question here, what do the following Z-scores mean? A Z-score of 0 just means that whatever score you got the average. Average score. So let's say, for example, here we've got this bell curve, our normal distribution. It's got a mean of 70, and it's got a standard deviation of 10. So we'll go 1, 2, and 3. Standard deviation 10, so we're going up and down by 10. So 80, 90, 100. 1, 2, and 3. 60, 50, and 40. So if you got a Z-score 0, it's like saying you got a score of 70. So let's say the average was 70%, and you got 70% in the test, you got a Z-score of 0. A Z-score of positive 1 means you're 1 standard deviation above the mean. So if the average was 70 and you got a Z-score of 1, because the standard deviation in this question is 10, that means you got 80%. Okay, so the average was 70%, you got 80%. Or if you got 80%, your Z-score would be positive 1. A Z-score of -2 means you are 2 standard deviations below the mean. So usually a negative Z-score is not that great. You know, you want to have a positive Z-score, but it really depends on the context of the situation. There'll be a question later on in this video where I'll go through one where a negative Z-score is actually a good thing. So if you got a Z-score of -2, when the mean was 70 and the standard deviation was 10, that means you got you got an actual score of 50. You got 50%. Okay, a Z-score of 1.4 means you're 1.4 standard deviations above the mean. So that's 0, that's 1, that's 2. 1.4, it's probably around here somewhere. 1.4 standard deviations above the mean. Looks like you got an actual score of 84. Okay, so let's have a look at the actual formula for calculating Z-scores. So this is the formula to calculate Z-scores. The Z-score is equal to the actual score minus the mean divided by the standard deviation. So this is actually on our reference sheet. So let's have a look for it. Here it is. This is on our reference sheet. So if you need to use it, you have it here. Now, it's good to know how to, have your algebraic skills, so you can just sub in values and you can find out either the actual score, or maybe you need to find the actual mean, or maybe you need to find out the standard deviation. Okay, you don't always have to just work out the Z-score. So we'll go through a few of those. So let's have a look at this question here. We've got, for a normal distribution, the mean is 62 and the standard deviation is 11. Find the Z-score for 84 and interpret this result. So we want to find the Z-score. The actual score is 84. So you got 84. The mean is 62, so we need to minus the mean. Then we need to divide that answer by the standard deviation of 11. So we put that in our calculator. We get 2. Okay, so you've got a Z-score of 2. So that means 84, or let's say this, a score of 84 is 2 standard deviations. 2 standard deviations above the mean. Alright, Ruby's Z-score for a class test was -2. What was the score if the class mean was 78 and the standard deviation was 6? Why don't you pause the video, have a go with this one yourselves. Okay, let's have a look at this one. So her Z-score is -2. What was her score if the class mean was 78 and the standard deviation was 6? So now we can just use our algebraic skills. You have -12 is equal to x minus 78. So x is equal to -12 plus 78. Which is 66. So Ruby got a score of 66. Okay, Micah's score of 48 is 1.7 standard deviations below the mean of 62. What was the standard deviation correct to 2dp? So he got a score of 48. The mean was 62. We want to work out the standard deviation, but we know that his Z-score is -1.7 because he got a score that is 1.7 standard deviations below the mean. So his Z-score is -1.7. So sigma has to equal to 48 minus 62 over -1.7. Okay, I just swap them two. Let's put that in our calculator. 48 minus 62 over -1.7, which is 8.24. Okay. A data set has mu equals 12 and standard deviation sigma equaling 3.6. Answer these questions correct to 2 decimal places. What scores will be 1, 2, and 3 standard deviations from the mean? So part 1, we'll look at 1 standard deviation. So a z-score of 1 is equal to a score minus the mean over standard deviation. So we can see 3.6 is equal to x minus 12. So x is equal to 15.6. However, this is saying that 15.6 is 1 standard deviation above the mean. This question just says from the mean. So technically, we can also work out a z-score of -1, because a z-score of -1 just means 1 standard deviation below the mean. So I'm going to apply the same thing to this. So negative 3.6 is equal to x minus 12. So x is equal to 12 minus 3.6, which is 8.4. So these two scores are 1 standard deviation. 1 standard deviation from the mean. It's just that this one's above it, this one's below it. And we can do the same thing for 2 and 3. So maybe I'll get you to pause the video, have a go with 2 and 3. Okay, so here are my answers for 2 standard deviations and 3 standard deviations away from the mean. So 19.2 is 2 standard deviations above, 4.8 is 2 standard deviations below, 22.8 is 3 standard deviations above, and 1.2 is 3 standard deviations below. Part 2, how many standard deviations from the mean are scores of 24, 11, and 7.7? I'll get you to pause the video and have a go with this one yourselves. Okay, here are my answers. So we have a score of 24 is 3.3 repeated standard deviations above the mean. A score of 11 is actually a z-score of -2.7. So that means 11 is actually 2.7 repeated standard deviations below the mean. And an actual score of 7.7 gives a z-score of -1.19. So an actual score of 7.7 is actually 1.19 standard deviations below the mean. Alright, let's move on to the third part of today's lesson, using z-scores to compare scores from different data sets. David compares his swimming times in freestyle and butterfly. In freestyle, he swam 35 seconds, and the club average is 43 seconds with a standard deviation of 4. In butterfly, he swam 37 seconds, and the club average is 46 seconds with a standard deviation of 3. In which event did David do better relative to other swimmers in his club? Justify your answer. So we'll have a look at this one. We'll look at freestyle. Let's work out his z-score. So we have his actual score of 35 seconds minus the club average of 43 divided by the standard deviation of 4. 35 minus 43 all over 4 is -2. Butterfly, his z-score is equal to his actual score of 37 minus the club average of 46 over the standard deviation of 3. So his z-score is -3. So in which event did David do better? Well, you're tempted to think that he did better in freestyle because -2 is bigger than -3. But in the context of this question, we can see that at negative, the more negative the z-score is, the better it is, because it shows that he's faster compared to the other swimmers. So David did better in butterfly relative to other swimmers. Than freestyle. A Z-score of -3 implies he is faster in butterfly compared to others than a Z-score of -2 for freestyle. So we can see here, right, his Z-score of -2 for freestyle is actually still very good. It shows that he's a lot faster than other swimmers. But because butterfly, he has a Z-score of -3, he's even faster than those in freestyle. Alright. Let's have a look at the empirical rules for normally distributed random variables to solve problems. So the empirical rule, or the 68, 95, 99.7 rule, states that 68% of data lie within one standard deviation of the mean. So here's our mean, and within one standard deviation, so from -1 to 1, what this is saying is that 68% of scores lie within -1 and 1 standard deviation of the mean. 95% of data lie within 2 standard deviations of the mean. So if I were to find from -2 to 2, all of that, 95% of the scores will lie from -2 to 2 standard deviations of the mean. And 99.7, if I were to do that, %, of the scores lie within 3 standard deviations of the mean. So there's still 0.3%, so that means 0.15% lie above 3 and 0.15% lie less than -3. Okay, so this is actually in your formula sheet here. We've got all the information here. It tells you approximately 68%, 95, 99.7, so you don't really need to memorize those numbers. But what I want you to memorize is this. There are 4 numbers that I want you to memorize because I think this will be very helpful when it comes to the HSC questions. Also because the fact that this topic, normal distribution, is a common topic between advanced and standard students. So it's likely that you'll be asked questions related to this. So this is what I want you to memorize, 4 numbers. From 0 to 1, it's 34%. From 1 to 2, it's 13.5%. From 2 to 3, it's 2.35%. And above 3, I said before, 0.15%. So these are the 4 numbers I want you to memorize, and it's going to be exactly the same on the other side as well. That will be 34, 13.5, 2.35, and 0.15%. Okay, so if I were to ask you, what percentage of scores lie between 1 and 2 standard deviations of the mean, it's just 13.5%. Or if I were to ask you, what percentage of scores lie greater than 1 standard deviation above the mean, it's all of this. We just add those 3 together. Okay, or you can do 100, or you could do 100% minus 50% and minus 34%. Okay, up to you. But these are the 4 numbers I want you to memorize. Okay. A machine produces cylindrical pipes. The mean of the diameters of the pipes is 8 centimeters, and the standard deviation is 0.04. Assuming a normal distribution, what percentage of cylindrical pipes produced will have a diameter less than 7.96 centimeters? Now, normally when I do these, I like to actually draw it out. So whenever I see the word normally distributed, or a normal distribution, I draw my bell curve, and I put my mean here. Now it says the mean is 8 centimeters, with a standard deviation of 0.04. So because of the bell curve up here, I can see it usually goes from -3 to 3. So all I'm going to do is I'm going to go 1, 2, 3, and 1, 2, and 3. And then I'll just label them according to my standard deviation. So my standard deviation is 0.04, so I'm going to go up and down by 0.04. Okay. What percentage of cylindrical pipes produced will have a diameter less than 7.96? So here's my 7.96. I want less than that. Well, if we've memorized our percentages, I know that's 0.15%, 2.35%, and 13.5%. So that means I'll just have to add them together. So 0.15 plus 2.35 plus 13.5 is just 16%. We'll have a diameter less than 7.96 centimeters. Okay. Here's a question from a past HSC exam. The weight of packets of Felicity's frozen fish fillets is found to be normally distributed with a mean of 512 grams and a standard deviation of 6. A wholesaler sells boxes of 40 packets of Felicity's frozen fish fillets. Given that each packet is labeled as containing 500 grams, how many packets in each box would you expect to be under the labeled weight? So as soon as I see this normally distributed, I'm just going to draw my bell curve. My mean is 512, and my standard deviation is 6. So 1, 2, 3. So that's 518, 524, and 530. 1, 2, and 3. 506, 500, and 494. Okay. Given that each packet is labeled as containing 500 grams, how many packets in each box would you expect to be under that labeled weight? So we want under 500. So I'm just going to label this as my 0.15%, 2.35%. So it looks like under 500 will be 2.5%. Okay, when we add those together, it will be 2.5%. So 2.5% of all the packets is what we expect to be under 500 grams. Well, there are 40 packets in the box. So we have 2.5% of 40, that's 1. So we expect 1 packet to be under the labeled weight of 500. So that means 39 of the packets should be at least 500 grams.